Alright, so this is a general chemistry problem. We're going to be doing a full-on titration problem today. Hopefully this will clear things up for you if you're someone who still struggles with titrations and buffer solutions and all that kind of stuff. Hopefully this will be a good overall video for you to watch in its entirety so that you can understand how to perform these example problems for your exams and for your homework. Let's dive right into this. So, I am going to be titrating a weak acid with a strong base. And perhaps in another practice problem, I'll do the opposite. A weak base with a strong acid. And so in this case, I'm going to be doing formic acid. Its pKa is 3.75, and its Ka is going to be this, because we can calculate the Ka value from the pKa value if you know how to do that. All we have to do is take 10 to the negative 3.75, or 10 to the negative pKa to get our Ka value. Now this is a really small value, okay? And remember the K value for anything, K solubility, Ka, K base, is K acid, K base, is going to be the ratio. This is basically the ratio of the products to the reactants, and since this is really small, the denominator is favored, okay? So what that means is that this is a weak acid. So if the Ka is really small, we have a weak acid. All right, so here's my situation. So I prepared in the lab 0.025 molar formic acid, and I have 0.1 liters of it, okay? So we can calculate the number of moles automatically, okay? And this will be helpful for us. The number of moles is just this times this. Okay, so the number of moles is going to be 0.0025 moles. All right, and then on the side, I prepared some sodium hydroxide solution. And this sodium hydroxide in solution is 0.125 molar. Okay? This is what I prepared in the lab. And so now I'm going to do my titration. So let's start by not adding any sodium hydroxide into this solution. And we're going to look at the moles here. So we have 0.0025 moles of our weak acid in our beaker. Okay? We have none of this in our beaker and none of this so far. So self-ionization basically means that the individual formic acid molecules are going to be sharing this hydrogen back and forth, okay? Until we get to some point where there might be a little bit of this in the solution. Let's see what that is, okay? And a little bit of this in the solution as well. So if we subtract X from here, okay, so we don't know how much is going to be self-ionized. We do the same here, but we have to add whatever we lose here, we gain here, basically. And we get 0.0025 minus X. And here we have X, and here we have X. Okay, so now I can do my calculation. The calculation I'm looking for, again, if you remember that the Ka is the products over the reactants, so we have X squared over this, but we're going to assume that this dissociates, that the number of formic acids that dissociate is really, really small. So we're going to assume that X is really small, so that if we were to subtract this from 0.0025, it doesn't really change this number. So we can simplify this by saying this, okay? We're just ignoring this X, okay? This is an approximation you'll make all the time in general chemistry. Now we could solve for X, all right? We know the Ka value, okay, and we know this. And so X is going to be the square root of this times this, okay? And then our pH is going to be the negative log of X, because X is the concentration of this. And so we get our pH is equal to 3.17. Okay, so I skipped a few steps here. Hopefully this will be good practice for you to see what steps I skipped. But again, all I'm doing is I'm solving for this equation. Okay, I know what my Ka value is. I know what this is. I multiply the two together. I take the square root, and then I take the negative log of my answer. Okay, and this is our first y-coordinate on our graph. Okay, now let's add 5 milliliters of NaOH. Okay, so when we add 5 milliliters of NaOH, so again, we start off with this amount of weak acid, and we're adding 5 milliliters of this, so that's 0.005 times our molarity, so times this right here. And what we get is 6.25 times 10 to the negative 4. Okay, we're not interested in looking at water here, because water is always in solution. And we have none of this so far. So I could subtract now, since this is the smaller number of the two. I subtract. Okay. Subtract, I have to subtract the same amount as I did there. Okay, and then I have to add 6.25 times 10 to the negative 4, like that. So I get 6.25 times 10 to the negative 4. This is 0, and this here is going to be 0.001875. Okay, didn't give myself a whole ton of space here, but now we can do the Henderson-Hasselbach equation on this. So the Henderson-Hasselbach equation, if you don't know already, is that the pH, so the pH is equal to our pKa plus the log of this amount over this amount. Okay? And so I'll erase that, and you could punch that in your calculator, and I'll just put the answer down, which is 3.27. All right, and actually I'm going to move this over here. So pH equals 3.27. Okay. So again, I'm not putting all my steps in here, hoping that you can be able to do this on your own too. I'm just going through the steps in my words here. All right, so the next step, if we come up here, I've pre-written some of the stuff out already, so this isn't too long and you're not super bored. So the next step here is we want to add 10 milliliters of our sodium solution. So here our x coordinate was 5, our y is 3.27. Here our x coordinate is 0 because we didn't add anything yet. We have 3.17 here. So we're slowly creeping up, which is good. But now, okay, so now our x coordinate is 10, and we want to see now what we do here. So again, we have 0.0025. Again, this is the number of moles that we started with, which is what I'm doing right here, this guy right here. And we are now adding 10 milliliters of NaOH, okay? And we know what our concentration is, and so that becomes 0.00125 moles. So these are, I'm doing everything in moles here. Okay. So now I can subtract, this is the smaller number, 0.00125, 0.00125, like that. Again, we're not concerned with water in this case, and then we have 0, and we have plus 0.00125. And then we can calculate these guys. So this becomes 0.00125. This becomes 0. And this is 0.00125. Now this is an interesting point. We have equal numbers of this. So when we do the Henderson-Hasselbach equation, so when we do this equation here, the Henderson-Hasselbach equation, pKa plus the log, what's this going to be? It's going to be the log of 1, because this over this is just 1. Okay, and the log of 1 is 0. So in this case, the pH is equal to the pKa. Interesting. And we remember that our pKa value is 3.75. Okay, and that's our next y coordinate. So we're slowly creeping up. Our next calculation, I'm just going through a ton of calculations here just to really help you understand how to do these kinds of example problems. Our next calculation is with 15 milliliters of NaOH. So what changes? So this didn't change, 0.025, and we have here 0.001875 this time. Okay, because this number is this 0.015 liters times our concentration. Okay? Okay, so we can subtract the smaller number again, 0.001875. And if you're not aware, these are ice tables, what I'm doing. I'm just doing ice tables with moles instead of concentrations, which is perfectly doable. 0.001875, and then no water, and we have to add 0.001875, like this. And what do we get? We get 6.25 right here times 10 to the negative 4. We get 0 here, and we have 0.001875. All right, we can do the Henderson-Hasselbach again because we have this in solution and we have this in solution. You can tell as we add more and more NaOH, right, this number gets smaller. The difference between the original amount and the amount and this new amount here, this is the amount that's eating up all of the NaOH. And as we add more NaOH, we decrease the amount of HA in our solution, which makes sense. Okay, we're slowly decreasing the amount of this in our solution. Okay, so we could do the Henderson-Hasselbach here, where this is in our log value. So this is what we put in, and this is what we put in for our Henderson-Hasselbach equation. And what we get here is that our pH is equal to 4.28. So there's our next y coordinate. Okay, now step 5. This is an interesting point here. We're going to add 20 mils. And what happens when we add 20 mils? Well, we have this much that we have this much of this, and when we add 20 mils, we're going to get 0.02 times this, but this is an interesting number because this number is 0.0025. Now that is super, super interesting. We have the same amount of NaOH as we do this. And so when we subtract, you can already see what's going to happen. We subtract, we get 0 for this and 0 for this. Okay, again, water, no. And we're going to add 0.0025. And we have 0.0025. Okay, so what do we do? Okay, so what we have to do is I am going to cram another equation down here. We have A minus now in solution with some water. Okay, and that is, now it's going to self-ionize. Okay, this thing is going to self-ionize into OH minus and some HA. Okay. Well, just like we did here for the self-ionization process, we come back to the self-ionization process, but it's just reversed because both of these were driven to completion, and this one is now at its. Now this is the only thing that exists in our solution. Okay. So what we can do is we can perform this calculation. We could perform this calculation. So we're not using the Henderson-Hasselbach in this sense, or in this step, because we don't have any HA. But rather, this is a KB now. This is a KB equation. And if we remember, KB is equal to the KW. So KB is equal to x squared over 0.02 liters. Okay, and where did I get this 0.02 liters? I'll back up for a second here, actually. So I got 0.02 liters because we added this much NaOH, okay, to an already existing 0.1 liters. Okay. So we have, if I were to be more complete, we have, I will make this a little bit clearer, running out of room here. So we have 0.0025 moles of A minus, okay, in a total of 0.1 liters plus 0.02 liters. And this becomes 0.02. Okay? This here. So now we can do the KB problem. The KB is equal to x squared over 0.02 liters. Okay. And remember the KB is the KW over the KA. So doing this calculation, we know this, we know this, we have this, we can solve for x. And when we solve for x, we get an OH concentration. So then we have to subtract that from our pH. So I'm skipping a lot of steps here again. But hopefully I'm skipping the steps that you will be able to do on your own. All right, what we get is that the pH is equal to 8.02. All right, that is our next y coordinate. Now I want to do one more, and that one more is on the second slide I made here. We want to add 25 mils. All right, well, originally we had 0.0025 liters, And this time we're adding 0.025 liters here. This is moles. I think I accidentally said liters. All right, and what we do is that we multiply that by the concentration of this that we prepared, okay, and we get 0.003125 moles. All right. So as you can see, 0.0025 moles. If we subtract that, subtract the same amount here, all right, we get 0. Here we get 0.0025, okay, and then here we get 0.0025, which is 0.0025. A lot of redundancy here, but I really want to go through a full-on example problem in pH. So what we can do now is we could say that the pOH is equal to the negative log of its concentration, because we have this in solution now, and this is just going to keep on getting bigger and bigger and bigger if we keep on adding more sodium hydroxide at this point. So we can virtually just take we can use this to calculate the rest of what we need. So 2.5. Okay, well that's the pOH. So the pH is 14 plus minus the pH. So it would be plus this because it's minus a minus. And what do we get? 11.39. So what does our curve look like? Okay, well, here's our pH curve, and it's going to look something like this. Okay. And what we have, so we have some interesting points. We have this point. We calculated this point here also. And we calculated some points before that. And I have them right in front of me here without having to go back to the original slide. We have a pH of 3.7. This is a pH of 3.75. This is the pKa value, 3.75. Okay, this is 3.17, which we calculated initially. Okay, at this point here, which is 5 mils, this is 10 mils of NaOH. At 5 mils, we calculated a value of 3.25. Okay. And then here at 15 mils, we calculated slightly higher. 15 mils, we calculated it to be 4.28. And then at 20 mils, we calculated a value of 8.02. And then at 25 mils, we calculated a value of 11.39. So this is a full-on calculation of pH. This is something you might not see anywhere else, but I really wanted to do this to really help you understand how these things are calculated. And I want to answer one question now, which is, what is the point of all of this? What is the point? Well, oftentimes we don't know what the pKa of a molecule is. Say we have some molecule and it looks like this. We know what it looks like, perhaps. And perhaps we got some stuff like this. And we have a weird molecule. I don't know, I'm having some fun here. We have this weird molecule and we want to titrate this thing. Okay, if we want to titrate this thing, and say we titrate this thing, we can create a solution of this. Okay, then we can take some NaOH, a known concentration of NaOH, and we titrate it. We stick it in we come into the lab, we titrate this thing, and it ends up maybe looking something like this. Maybe it ends up looking something like this. These are the points we're interested in. These are the points we're interested in. Okay, these are going to tell us some pKa values. This is our first pKa value. This could be, if this is what it looks like, this means it's a polyprotic weak acid. Okay? This might be our second pKa value. Okay, so this might have something that looks like this. We have our MlNaOH. We have our pH. Okay, so when we titrate something, when we're titrating some molecule, okay, we create a known thing of sodium hydroxide, NaOH, and then we have this in a beaker. Okay, we have this stuff in a beaker. All right, we can titrate this to produce this graph, and then we can know our pKa values. That's why you see, that's how we discover these pKa values. Okay, and we can also discover more things about this molecule by doing titration analysis on this thing. But this is a long video, and I hope it serves you well. If you like the way I teach, please visit my website at tristancarmacy.com. And if you want to keep on seeing more content, then you can visit my Patreon page as well. And I wish to see you in the next one.